So next one is Professor Raphaële Clément from the Material Department of the University of California in Santa Barbara. She did his Ph.D. in chemistry at the University of Cambridge with Professor Clare Grey, that she gave his talk yesterday. And after that, he pursued a postdoc at the University of California in Berkeley with Professor Gerbrand Ceder, and now I have already said he's professor at the Material Department of the University of California, Santa Barbara. He is a specialist in magnetic resonance spectroscopy, in situ experiment, in operando experiment also, and he's interested also in first principle calculation. So, Raphaële, is your turn.
So thank you very much for giving me the opportunity to talk today. Good morning, everybody. Good afternoon. Good evening. So today I'm going to talk about some of the recent work we've done on a novel type of lithium-ion cathode, which are transition metal oxides, but with a cation disordered structure rather than a layered structure. So to start my talk, I'd like to first discuss layered compounds that you're all familiar with. So these are the NMC type cathodes that you are familiar with. And so these types of materials are popular because the layered structure enables facile lithium extraction and reinsertion during charge and discharge from the lithium layers in these materials. However, there are certain shortcomings of these compounds. And one of the major shortcomings is this large volume change as you extract lithium from the lithium layers. And this, so you get an expansion of the structure along the C-axis, which is perpendicular to these layers here. One of the other aspects of these materials, and that was covered very well by Professor Monte, is that they rely on the on manganese, on cobalt, and on nickel, because these particular ions have a very strong preference for octahedral site occupation, and so this prevents these transition metals to go into tetrahedral sites in the lithium layers and eventually into these octahedral sites in the lithium layers. Which would then result in some rock salt type structure or a spinel structure, and therefore change the properties of the material. So by relying on these three compounds, we can mitigate these issues. However, at high voltage, you can still get partially some phase transformation to these compounds. So having well-ordered structures in the battery field has, for a very long time, been seen and considered as an important factor for high capacity and for good cycle life. However, in the last 5 years or so, as part of the community has been interested in cation disordered compounds, and this is really questioning the cation ordering paradigm for the design of lithium-ion cathodes. And so this work started with a nice paper by the Ceder group. And what they made here, they made a lithium molybdenum chromium oxide compound as a layered compound initially. And you can see it from the STEM images shown here. So you start with a really nice ordered compound where you have these lithium layers in dark and the transition metal layers in lighter colors. But as soon as you start cycling it, the material disorders. And so after one cycle, you can see disordering here, which becomes a completely disordered structure after 10 cycles. However, the surprising observation in this paper was that the electrochemistry is actually quite good. You can definitely see a change from the first charge to subsequent charge-discharge cycles, but the capacity itself isn't fading too much, and it's also fairly, you can extract more than one lithium per formula unit. So this is a good cathode despite the disorder. And so what this suggests is that there is a different type of lithium diffusion mechanism in these materials. So we're not relying anymore on these, what we call one transition metal channels. And so the reason why we call these this way is that for lithium to hop between an octahedral site to an adjacent octahedral site in the lithium layers in your layered compounds, it has to go through a tetrahedral site here. And in this case, this tetrahedral site has 4 faces sharing 4 octahedra. 3 of them are lithium, and 1 is a transition metal, which is why we call this a one transition metal channel. This is the normal path for lithium diffusion in layered compounds, which very much relies on this the size of this tetrahedron. In the case of disordered Roxel compounds, now you have disorder, and so you can have these tetrahedral sites that are surrounded only by octahedral lithium sites. And so these we call zero transition metal channels, and it is believed that these types of local environments or channels are the ones that allow fast lithium diffusion in these cation disordered compounds. So we need to rethink a little bit how we visualize diffusion in these materials. So over the last 5 years, as people have learned more and more about disordered Roxel compounds, a few design criteria have emerged. One of them is that in order to stabilize a cation disordered structure, such as this one, where now you no longer have a transition metal layer and a separate lithium layer, you need to introduce transition metal species that can accommodate highly disordered octahedral sites. And the reason for this is that now that you don't have these layers, the octahedral sites in all of these layers will be slightly distorted. And so we need some transition metal species such as molybdenum 6+, niobium 5+, titanium 4+, zirconium 4+, which have no d electrons to accommodate these distorted sites and enable redox active species, such as manganese, for instance, to occupy more regular octahedral sites. And so that stabilizes the structure. Another important design criterion is the amount of lithium that we have in the material. And lithium excess is needed in these particular materials to allow for good lithium percolation. What that means is long-range lithium diffusion relies on the connection between lithium sites here that are percolating through the structure. And for this to happen, we need some excess lithium. So if we want to rewrite the general formula of these materials, we have lithium with some excess. We have a transition metal redox active species. We have a non-redox active transition metal species, which is here to stabilize the structure. It's usually a high valent D0 metal. And so what this shows us is that, first of all, we are reducing the average cation valence by having this excessive lithium. But this cation valence reduction is compensated by the fact that we now have also high valent cations. So overall, we can keep charge balance by compensating the excess lithium by some high valent cation. This high valent cation also has a second use here, which is that by having more high valent transition metals, we can reduce the oxidation state of our redox active species, which means that we can increase the redox reservoir, the transition metal redox reservoir of our material. One interesting property of these materials, these disordered Roxel compounds, is that they can incorporate fluorine. So you can substitute a fraction of oxygen by fluorine in these materials, which is something that's not possible in layered oxides. And you can understand this simply by thinking here that your fluorine transition metal bond is much higher in energy than the lithium fluorine bond. And in layered oxides, you need to produce 3 transition metal fluorine bonds per fluorine substitution. Whereas in cation disordered compounds, you can have fluorine sites or anion sites that are almost all surrounded by lithium. So you have these lithium-rich environments, which are the ones where fluorine will substitute for oxygen preferentially. Why is fluorine substitution an important factor for these materials? Well, what we found here, and this is a work that was comparing 2 cathode materials, both of them have very similar chemistries, but one is an oxyfluoride, so we've substituted some oxygen, the other one is a pure oxide. And if you compare the performance of these materials, and these are not the best performing materials, by the way, this is just an example, but this clearly shows you that you have reduced polarization as you substitute with fluorine, and you have reduced irreversibility. Another benefit is that you're increasing the average potential of your cell, of your cathode by substituting with fluorine. And this leads to an energy density that rises here by from 590 watt-hour per kilogram to 790 watt-hour per kilogram. So this is showing you the performance of these materials, and this is a table, or I guess a plot that's showing the voltage of various lithium-ion cathodes, their specific capacity, and if you take the product of these two parameters, you get the energy density, which is shown with these dotted lines here. As you can see, and compared to state-of-the-art commercial cathodes, some of our disordered Roxol compounds are performing very well. And so some of these materials have energy densities up to 1,000 watt-hour per kilogram at this point. And it's still relatively, it's a relatively recent field, so performance improvements are likely to occur. Perhaps the most important aspect of these materials is that we can now use cheap and abundant metals. So we are no longer constrained by using manganese, cobalt, and nickel. We can now start exploring compositions where manganese is the only transition metal that is redox active, and we need to combine this with one of these D0 metals to stabilize the disordered structure. Okay, so this is giving you an overview of the performance of these materials. However, there is a lot of research and development ongoing here, and the main point here is that the characterization of these materials is particularly difficult. Cation disorder in this case leads to several transition metal environments, and these have very different redox potentials. And so often the classical characterization tools that we use in battery research are not suited for looking at local electrochemical properties, which is what happens in these materials. Other downsides of these materials is that we're really trying to understand where fluorine incorporates the structure, what type of short-range order it leads to, but X-ray diffraction, neutron diffraction are not amenable, and they cannot distinguish between oxygen and fluorine. So we need to think about new characterization techniques to really understand the structure and the redox properties of these materials. And one technique that has emerged here that is particularly useful is solid-state nuclear magnetic resonance. And when it is combined with first principles calculations, it becomes a powerful tool to study these materials. So today I'm going to answer a few questions about these materials. One is, does fluorine actually incorporate the bulk structure of these DRX compounds? What is the fluorine solubility limit of these materials? To what extent and what type of cation short-range order are we seeing in these DRX compounds? And how does that impact lithium diffusion and electrochemical properties? And finally, how does fluorination affect short-range order, lithium diffusion, and the performance? So to give you a very brief introduction to solid-state NMR, so this is a local structure technique. So it's sensitive to the environment around the nucleus species we are investigating. And the chemical shift, which is the position, it gives you the position of the signal in the spectrum. This chemical shift provides information about the local environment of the nucleus species. So if we start with a very simple example here, this is lithium fluoride. This is the environment of fluorine in this material. So we have fluorine here in the middle, and this is a 5 angstrom sphere around this fluorine atom. So this is its local environment. And that local environment dictates the chemical shift that we see in our spectrum here. These asterisks above these little signals here mean that these are sidebands. And so this is the main peak that you should focus on here. So in lithium fluoride, you have a single fluorine environment, which is surrounded by diamagnetic species only. So you have this very short, sharp signal at a chemical shift of -204 ppm. But what we are really interested in here is understanding the local structure of our cathodes. And so this is a particular cathode shown, the composition is shown here. This is a DRX compound, a disordered Roxol cathode. And in this particular material, you now have fluorine environments that have 3 coordination shells with different cation species, illustrated in light blue, in dark blue, and in red. So you've got these 3 coordination shells. And within these 3 coordination shells, your fluorine can be surrounded by lithium, but also by nickel, molybdenum, and titanium based on this composition here. So the number of local environments will be much larger in this material. And the way you need to understand these spectra is by understanding that the paramagnetic nickel ion, which is the only paramagnetic species in this material, will result in signal broadening and a large shift of the resonance away from the position of this resonance in LIF, which is why we see this much broader signal here. The reason for this is that your nickel has unpaired electrons in its d orbitals, and these unpaired electrons have a spin which interacts with the spin of the nucleus species we're looking at. And so this interaction is very strong. This is your fluorine, this is your nickel. This interaction is very strong and leads to broadening and a chemical shift. It also allows us to gain a lot of information on the local structure of these materials based on the chemical shift. But the complication here is that we have a disordered structure and therefore a large number of environments with overlapping signals. So if we just compare these two spectra, what can we say about the integration of fluorine in the DRX structure? Well, we can see clearly that the signal changes from going from LIF to LNF15. LIF is the precursor in the synthesis of these materials. So we do have some intensity at the position of LIF, which suggests that we have some residual LIF in the material, but we also have a wide range of other environments here with different chemical shifts, which suggests that we have successfully incorporated fluorine in the DRX structure. But to learn a bit more about these materials, we need to complement our experimental data with first principles calculations. One of them is understanding better the NMR properties of these materials, but also understanding the favorable distribution of fluorine environments in this material. So we carried out this type of analysis for this particular composition shown here. Again, what we are looking at here is the strong interaction between our fluorine nucleus that we are probing with NMR and its interaction with nickel ions that are nearby, and especially the electrons in the d orbitals of nickel that are delocalized onto the nucleus of interest. And so that delocalization process leads to a non-zero spin density at the position of the nucleus, shown here. And this is something we can calculate from first principles, and it gives us an idea of the chemical shift that we would expect for that particular environment. So what I'm going to show you right now is what happens when you have nickel directly bonded to fluorine, or what happens when it's further away from the fluorine in the second coordination shell or the third coordination shell. What we found from DFT is that if it is directly bonded to fluorine, it will lead to a very large chemical shift and a very broad signal. If it's further away, so in the M2 position, M3 position, which are your second coordination shell and third coordination shell, the chemical shift should be much smaller, and the broadening is not as significant. And so what this really tells us is that what we are seeing experimentally is likely not coming from fluorine that are directly bonded to nickel, because these signals are too broad. So this already gives us information about what we can learn with NMR spectroscopy on these materials. But this is not the complete picture here. We also need to know the most favorable distribution of fluorine sites in these materials from Monte Carlo simulations. So here we did two simulations, one at the synthesis temperature of these materials around 1,000 Kelvin, and one at very high temperature to mimic the statistical limits. And what we're comparing here is the distribution of fluorine environments under these two conditions. So one is the random distribution of cation species, and this is for the distribution that we expect in our material. So here is a plot showing the frequency of different types of fluorine sites in this material that have been categorized as a function of their interaction with nickel. So these ones have one nickel directly bonded to them. These ones have two nickel directly bonded to them. These ones have no nickel directly bonded to them, but nickel in the second coordination shell. And these ones have nickel in the third coordination shell only. And what we find is that in our material, we have clear short range order. And so fluorine here has very few nickel nearest neighbors directly bonded to it. And instead, if we look at the distribution of fluorine as a function of the number of nearest neighbor lithium, we find that fluorine will substitute for oxygen in these lithium-rich environments that I discussed at the beginning of this presentation. So there is clear short-range order in this material, and fluorine is integrating the structure in these lithium-rich environments, either with 6 lithium nearest neighbor, 5 lithium nearest neighbor, or 4 lithium nearest neighbor. So going back to our initial analysis here of this cathode material, we can now say that the spectrum that we see is only coming from fluorine nuclei with no nickel nearest neighbor. This is what we found with our first principles NMR calculations. But we also find with our Monte Carlo simulations that this is, we're actually able to see still 80% of the fluorine in this material, because only 20% of the fluorine is directly bonded to nickel. And so we are sensitive to most of the fluorine in the material. Most of them are surrounded by only lithium, or by 5 lithium and another transition metal species. So this particular study went very much in depth into trying to understand short-range order. This is very much relevant for electrochemical performance because short-range order here is pervasive in DRX compounds, and it does affect lithium diffusion. It does affect the electrochemical performance. So this was an interesting study that was done with the Ceder group here a few years ago, comparing two disordered rock salt oxides. They have very similar chemistries. The only difference here is the D0 transition metal. Here it's titanium 4+, and here it's zirconium 4+. And so what they found is that if they took an electron diffraction pattern of the two compounds, they found diffusive reflections here, which suggest that there is short-range order in these materials. Short-range order is different in these two. As you can see, the patterns are slightly different. And when they simulated these two materials with Monte Carlo simulations and reproduced the electron diffraction pattern that they expected from these simulated structures, they found very good that they match very well the experiments. These Monte Carlo simulations are useful because they can give you a distribution of local environments. And here we're looking at the local environments that allow lithium to diffuse. So if you remember, I told you that these zero transition metal channels are important in these cation disordered compounds because these are the ones that lead to fast lithium diffusion. This is showing you the relative occurrence of these channels compared to the random limit. So if we had no short range order, and this random limit is shown by this dotted line here, what we find is that for both of these materials, we have fewer of these zero transition metal channels than we would expect in a random distribution of cations. So this is not a good news for these two materials. And if you look at the electrochemical performance now compared between room temperature and 50 degrees Celsius, you find that you have a large increase in the reversible capacity if you elevate the temperature, which suggests kinetic limitations for both materials, which is consistent with the fact that they have few zero transition metal channels. And this is even more pronounced for this zirconium compound. So understanding short range order is extremely important to optimize these materials. What has been found, and this is a work that I've been involved in recently, this came out a couple of weeks ago. Here, we're trying to find solutions to reduce the short range order. And one of the solutions that came up was high entropy. And this is a notion that's used very much in the field of alloys, where high entropy alloys are used to obtain a uniform distribution of transition metal species. So here, this is something we can use to reduce short range order in these materials. And so here we are comparing 3 different compositions with an increasing number of transition metals. And as you can see, from the electron diffraction patterns and from the integrated intensity, we are seeing a clear reduction in the short range order as you go to more transition metal species. This is translated into better electrochemistry. So as you can see, these 3 materials were cycled between 1.5 and 4.7 volts. The one with the most transition metal species has a higher capacity. It also has a much higher rate performance. And this is the first instance where we have such a good rate performance for a disordered rock salt compound. Here, this is about 8.5 C charge-discharge rates. And as you can see, we still obtain 170 milliamp hour per gram of capacity, which is very significant and much better than the one with fewer transition metal species. So that suggests that high entropy is a strategy that's valuable for high energy density, but also for capacity rate performance, sorry. Our NMR data shows that fluorine has incorporated these three materials very well. We have very little lithium fluoride left in these materials. I will say here that we tried to look at short range order with lithium NMR. This does prove to be difficult for most materials because of disorder that reduces the resolution of our spectra. So we are looking, and this is unpublished work, this is very recent work, we're looking at specific compositions that allow us to probe the local structure in fine detail. And so here we've eventually managed to make some materials that now we can start distinguishing many different environments in the lithium spectrum, and corroborating this with first principles calculations. Our hope is to build a detailed structure, a detailed model for the local structure of these materials, so better understand short range order. We're also looking at 2D NMR spectra, which allows us to look at lithium fluorine proximities. And this is important, as you know, because short range order is leading to these lithium-rich fluorine environments. So we're really trying to dig deep into the structure of these materials. So just to finish with an important point here. So we have been involved in the study of these two very promising disordered rock salt compounds. And I'd say they're very promising because they rely on manganese redox, and they rely on high fluorine contents here. And this high fluorine contents allows you to reduce the valence of the manganese down to manganese 2+, which is also charge compensated by the fact that we have a high valent D0 metal here. So we have a lot of manganese 2+ in these materials that can be oxidized all the way to manganese 4+, which is very rare in these oxides and oxyfluorides cathodes. And it allows us to really leverage transition metal redox capacity here. And so you can see clearly that the initial capacity of these materials is very good, better than the theoretical capacity based on manganese redox. Cycling performance, long-term cycling stability is still something we need to work on. But what I want to stress here is that from NMR, we clearly see that we have quite a bit of LIF left in these materials. As you can see, this is these sharp peaks, this envelope of sharp peaks is showing you how much LIF we have. We also see this from our lithium NMR data. And what this suggests is that, well, first of all, fluorine solubility is clearly limited in these materials, and we haven't actually figured out yet what is the optimal fluorine content. But also it suggests that these materials can perform very well, even though we have quite a bit of LIF left in the sample. So we're looking more into these questions of the optimal fluorine substitution level, but also how LIF is impacting performance. Is it actually helping the cathode material by creating this coating layer that prevents side reactions with the electrolytes? That's one of the working hypotheses. So I'll just summarize here by saying that these materials are relatively new. They've been researched for about 5 to 6 years at this point. They are promising cobalt-free alternatives to layered transition metal oxides. And so far, they have achieved up to 1,000 watt-hour per kilogram of energy density. They rely on sustainable chemistries such as manganese, titanium, etc. They also enable bulk fluorine substitution for oxygen, which results in more stable electrochemical cycling. Short range order is still a question mark here. This is a phenomenon that happens in all of the DRX compounds, and we're trying to control it and better understand it. It can be reduced by going to high entropy cathodes, which also improves rate performance and energy density. So there are still a few unanswered questions on these materials. One is, what is the optimal fluorine substitution level? What are the major degradation pathways for these materials? And how can we improve long-term cyclability? So there is still work to be done, but these the start looks promising. So on this, I'd like to thank my group, especially those people who've been involved in this work, Reynolds, Emily, Howie, and Yuefan. And I'll thank my collaborators at Berkeley, the group of Gerbrand Ceder, especially Zhengyan, Daniel, Jinyuk, and Huiwen, and funding from the DOE and UMICOR. Thanks.